Professor Cary Mitchell, Department of Horticulture and Landscape Architecture at Purdue. He's been at Purdue doing plant physiology work since 1972 and has a vast experience in all kinds of situations, and he'll tell you about some of those today. In the title of his talk, he says, Growing Food Indoors Year-Round with Lessons Learned from NASA. So I'll turn it over to Cary.
All right. Hi everybody, I'm glad to be here with you today, and thanks to Gus for thinking about me. Since I've been at Purdue in the Horticulture Landscape Architecture department, I've become very involved in something called controlled environment agriculture. And for a long time that was a fringe activity. But I became involved with NASA very early in my career, and was the very youngest of a group of investigators who became involved in pioneering bioregenerative life support systems and advanced life support systems for habitation at distant space destinations. I'm the only one left now, actually. So, and I've really seen this fringe area of CEA become mainstream. I was just in Washington, D.C. last week at the annual conference of the American Society for Horticultural Science, and we had 5 entire sessions just on CEA, Controlled Environment Ag alone. So it's gone from nothing to a mainstream phenomenon, and a lot of that is thanks to NASA for some of the pioneering work that some of us were able to do early on in that. I also caught a summer cold last week in Washington, D.C. Very cold hotel air conditioning, but I know it takes more than that too. But thankful for the microphone working, and I've got my water glass handy here. So, I don't know if you'll be able to see the pointer very well, but here is not on the screen. So here's a depiction of a crude lunar base, and with cutaway views. These are cutaway views, so you can see inside the very thick habitat that is constructed of concrete made from lunar regolith, or soil. It compacts very easily, and it has to be meters thick to afford any protection from ambient space radiation, and also from the craters from the meteorites. The moon is still bombarded regularly by meteors and meteorites, and so any direct hit on a module would take it out. So this is just one scenario. They also depict people habitating lava tube caves from the days when the moon was still volcanically active and there was lava running on the surface. Same thing for Mars. Here's a cutaway view of a berm at a Mars base. And interestingly, they're also depicting channels from running water maybe many millions of years ago. But anyway, you see this depiction indoors of trays of vegetables. And both on the moon and on Mars, these are not going to be lighted by the sun. It's too dangerous. You can't have greenhouses up there because of the high ambient radiation levels and the particle impact dangers. So they're either going to have to be underground or heavily bermed and so on. But it does raise the specter of what it's going to take to grow food. And it's going to have to be grown indoors, obviously. Okay? So here then is a summary of what I worked on with this other group for many years. This is called a closed bioregenerative life support system. And it's the same as what Earth does now, the Earth's biosphere. But at the heart of the life support system in space are green plants, photosynthetic green plants. And their photosynthetic process in the light is exactly opposite what humans do in the light or the dark. Respire. We inhale oxygen, we give off CO2, plants do the opposite and the light. So you put the two together in a system that is closed with respect to mass, and you at least potentially can create a dynamic equilibrium. Well, if you're going to really close that off on Mars, and it's way too expensive, and there are not frequent enough opportunities to resupply all of the life support consumables, these space bases are going to have to be sustainable on their own. So you're going to have to grow your food, grow your oxygen, and recycle your carbon. So the crew makes waste, wastewater, solid wastes, it gives off CO2. There will be bioprocessing going on. And so a very simplified loop shows what's going on in it. So all of the mass recirculates, recycles, but energy has to come in from the outside, either in the form of sunlight, nuclear energy, or whatever, and there will be some waste heat energy that will go out of the system, just like it does on Earth. But it's going to be much more complicated to do on a small basis where you're controlling it and engineering it. So this takes many years of development, and we started that back in the 1970s, but NASA, being an engineering, managerial, very political agency, priorities kept changing. So they would stop, they would start, they would stop, they would restart. And it really drives you crazy. But anyway, while I was doing that, and this is the only slide I'm going to show you that has any numbers on it. You won't be able to see all of them. But on the left column here are crops. These are common field crops and also some common horticultural crops. And then we're showing their cropping time and their yield for two forms of agriculture. One is called open field agriculture, OFA, and the other is controlled environment agriculture, indoors, either in a greenhouse or a warehouse. And these are old numbers, but what we noticed is that you can grow crops much more quickly indoors than in the field. There's no stress. There's no cold days, there's no cloudy or rainy days, so you can keep the plants out of stress and you can give them an optimizing environment. And as a result of that, the number of cropping cycles per year goes up indoors too. So there might be only one or two opportunities in the field to grow something, but in the greenhouse or in a warehouse even, it can be many more times that. And so when you multiply those two together, you get numbers that have been displayed here in the right-hand column called fold increase of CEA over OFA. And even though these are old numbers, they kind of average out to about an order of magnitude increase in crop productivity over the course of a year for indoor grown crops. Some of these numbers have come way up since then. They were not optimized. I took them out of the literature as I could find it. But for example, with tomato, I found data for determinate tomatoes. So you could get 5 cycles per year, and you could get the crop coming in within 67 days rather than the 160 it would, rather than the 160 it would take in the field. But things have moved on today, and in greenhouse agriculture, for example, tomatoes, we're not growing 5 crops a year, we're only growing 1. But they're not determinate varieties anymore. This one you see on the screen here is indeterminate. It's like Jack's beanstalk. It grows constantly. So they flower and fruit from the bottom up. You harvest and defoliate from the bottom up, and the stem gets like rope. So you coil the rope, and then you lower and lean, or you keep it attached to a wire maybe 20 feet above the floor of the greenhouse. Now this is a nice picture, obviously taken with the sun directly overhead. You can see all the detail in there, but here in the Midwest, we're in what we call the cloud belt. And here's an image of the top of a tomato canopy growing inside a greenhouse, and only the tips of the leaves are in the sunlight. And that sunlight moves from the east to the west all day. Sometimes it's cloudy, sometimes it's winter, and you don't have enough light to grow the crop. So they put overhead high-pressure sodium lamps. It's daytime, so they're not on right there, but you can see the large separation distance between the lamp and the top, and that's because they're red hot. They're the types of lamps you see illuminating streets and cities at night. They have a lot of thermal radiation energy. So if you look at this down at the bottom of the canopy, here's one in summer on the left, and only the upper leaves are shaded. You can see some fruits down in there. It's so dark down at the bottom of the canopy, these plants can't grow. And the fruits are not growing, they're not ripening very well. Now, same thing in the winter on the right here, and you can see one of those high-pressure sodium lamps illuminated in the background. It's the bright yellow, intensely yellow thing. So there's a lighting problem. So in some of my work for NASA, I started working on intra-canopy lighting with vertical, and you put it right into the canopy, right? No, not with high-pressure sodium. It would burn the plants. So we knew that NASA was interested in light-emitting diodes, the cool LED lights, so we made vertical towers of the LEDs. And here, in the greenhouse at Purdue, we have 2-foot segments of LEDs irradiating in both directions, and that the section at the top is not illuminated yet because the top of the plant hasn't grown up into it yet. But on the right, you can see what looks like Christmas trees. That's a whole row of high-wire tomato plants, and the light is coming from within. We don't need any of that bright, hot, expensive overhead light. So we're able to get large increases in fruit yield compared to no supplemental lighting, but for only half the cost, half the energy cost as what it takes with those yellow overhead lights. So there's real potential for energy savings there. Now another type of indoor grown.
Could you hold the microphone up, please?
Very popular today is leafy greens, and like these lettuces growing hydroponically in a greenhouse, and they grow a lot faster. They'll maybe have in the greenhouse a cropping cycle of 40, 45 days instead of longer than that. And you can put them in sectors too with nutrient film technique hydroponics. Just in case a disease gets in there, it would spread to all the plants. So they have sections just to make sure it stays disease-free. And you've heard a lot lately about lettuce being recalled from the grocery stores. Well, that's been outdoor grown in the field, and hydroponics in the West has been contaminated by animal feedlots. Even birds flying over, bird droppings contain E. coli. And so it's very easy for field-grown crops to get contaminated and to get recall. You have a much better chance of sanitation and protection in the greenhouse. And then here are some examples like of A-frames where they have strawberries growing very, very densely, very productively. Here's another A-frame with leafies in a greenhouse for aeroponics on the left. And aeroponics is a mist of nutrient. It comes on every few seconds, keeps the roots wet, and then it drips off and is collected and gets recycled, pumped up and recycled. Same thing. Perhaps some of you have traveled to O'Hare Field in Chicago and seen this O'Hare demonstration of the aeroponic towers. Have any of you? You've seen that? Have you? Yeah. It's up on the second level and right in the middle of the terminal. And what they're doing is they're using recirculating aeroponics there, pumping the liquid up to the top, and then it drips down as the mist keeps the roots wet. Well, notice, something I noticed is that, and these are high pressure these are high-intensity discharge lamps up there, but it's much brighter at the top than it is at the bottom. So you see a lot of vegetation at the top, and it really thins out near the bottom. So there's a real drop-off of intensity. Commercially, that would not make money. But as a demo in the airport, and all the restaurants take that produce and they sell it, in their restaurants. The businesses there. Okay, so now back to some of my NASA work. 20 years ago, I went to the hardware store and got Raingo plastic house guttering, turned it horizontal and made recirculating hydroponic systems out of it. And then we were growing leaf lettuce hydroponically, recirculating in a growth chamber. That's what this is. And typically in hydroponics, it takes 30 days to grow a leafy green lettuce crop. This is at day 16 from seed. It's just starting to go exponential in its growth curve. And then 5 days later, it looks like this. It just completely grew together. The canopy is closed, and we had to harvest. So using the optimization protocols we developed for NASA, we were able to harvest the crop in 22 days instead of 30, which is what's done commercially.
The lettuce you get in the grocery store that's in the tub that does you got to have the root ball. Is that a hydroponic lettuce like you grow in here?
Well, some of them in the grocery store you buy actually will have a little container on the bottom. This didn't have this. This is recirculating nutrient film, so they would just bear root in a very thin nutrient solution.
Okay.
Yeah. Gail?
Does it change the flavor? Is it different flavor than what we are used to?
It's what?
Do the vegetables do they taste a little bit different than what we have?
They can. They can taste better. They can taste worse. I'm not sure I'll have time to get into that part, but today with LEDs, at the end of the hydroponic cropping cycle in a warehouse, they're actually upping the blue light, bringing out the phytochemicals, bringing out the anthocyanin pigments, and it may be healthier, it may not, but they're sure using it for marketing possibilities. Yeah. So anyway, let me go on here. So what's happening today is something called vertical farming in warehouses, and you can't afford to have hot overhead lights. You've got to have brightness. So you bring in your light-emitting diodes again. I think they were born for this. They're fairly cool in temperature as well as in operation. So, yeah, but what I see when I visit the vertical farms is that they have too much space between the tiers. And these are hydroponic below. You can't see it, but it's recirculating solutions. And here last October, I visited Aero Farms in Newark, New Jersey. They're a huge warehouse. And here's a 69,000 square foot warehouse where they have 12 racks high. So it's 69,000 times 12. And, I talked to you earlier about CEA maybe having an order of magnitude, a 10-fold greater productivity per footprint. Well, these vertical farms have 100-fold because it's not just one level. They're stacking them up 10 and 12 high. And this is aeroponics there, and they have mist below. And then at the end of these are baby greens, so they're harvested in 16 or 17 days. They're washed and they're put into these clamshells that they put on the grocery shelves, and sells for about $3.99, but it's only 5 ounces inside. So I figured out they're having to make around $16 a pound to make a profit on this. So here's the problem with controlled environment ag. It's high tech, it's highly productive, but it costs a lot. And this is where the challenge is, and this is where I'm putting my research energy in right now to help solve some of those problems. Okay, and I keep going back and forth between the present and my NASA research. This is back to our NASA research a few years ago, where we were taking LED arrays of red and blue. Those are the two wavelengths that are the most efficient in driving photosynthesis. And we're bringing the array close to the crop. So this is a hydroponic lettuce crop, and we've got the, maybe 15 centimeters above it, we've brought in the LEDs. And because it's close, we don't need as much power to get the same light intensity, so we're able to dial them down. Our research LEDs are tunable, both in color as well as intensity. So we've been able to save a ton of energy by going to something called closed canopy lighting. But I wasn't satisfied with that, because look at the photons, the pink color falling between the plants. If it's not falling on vegetation, it's being wasted. So I'm going to skip this one, come back maybe later. So in this, come back later. So what we did, we developed a targeted lighting system. So it would automatically detect where a plant is and how large the plant is, so that every day we re-image that plant, and if it's larger, a few more LEDs in the cluster above, in the array above, are energized, come on. But we're not wasting photons of light. Photons of light require electricity. Electricity costs money. So we're trying to really cut back on that. So, since 2006, NASA put all of this work on the back burner, but we've managed to get some of it starting to come back slowly. And I'm part of a grants program now that is feeding information to the veggie plant growth unit that's now growing vegetables for the astronauts on space station. And this is an actual picture of veggie on space station. And it's a kind of a transparent cellophane-like accordion container with an LED array at the top and vegetables growing hydroponically below. And we're developing on the ground growth protocols for the LEDs, for fertilizers, for capillary wicking of water. And this is going on in our lab at Purdue right now. We have 6 of these veggie analog systems in our walk-in growth room that the grad students are working with, trying to optimize. And then the astronauts adopt those protocols when they fly that crop in space. This is Mizuna, which is growing on the International Space Station right now. To end, I want to talk just for a minute about this nascent vertical farming industry, grown in warehouses. It has a lot of potential, but profitability is very elusive there. And here's a cartoon that I prepared. The square is a warehouse, and here's just 2 racks of vegetables growing hydroponically. And the LEDs are being energized by the electric grid. So you've got high power electricity coming in, there's a transformer tower, changes it into low voltage DC, and then it powers these LEDs. Well, if you fill a warehouse with racks of vegetables, like this room or that Aero Farms warehouse with all, 69,000 square feet times 12, and fill it, the carbon dioxide in the room will be drawn down in minutes, and the plants will stop growing. CO2, even in this room with a lot of people in it, it's a trace gas. And the problem is in photosynthesis, the plants take up CO2 in substrate amounts. So the vertical farmers are having to use bottled CO2, plus they have to keep the vents open, where you have CO2 coming in on the left, and these plants are transpiring clouds of water vapor, making the building very humid, causing tip burn of the lettuce. So they've got to have the vents on the other side open, and they're venting out water vapor they're venting out the waste heat from the LEDs, and they're even wasting some of that CO2, some of which came from bottled. So this is not a sustainable system. And so I'm proposing to NSF right now this type of a system. In the urban areas, we take food process waste, and for example, like in Indianapolis, Indianapolis Fruit, they generate 30 tons of food process waste a week, and they pay $1,000 to have it trucked off to the landfill, to have it buried for them. Well, I say collect that in the cities and then have AD, lower left-hand corner, anaerobic digesters without oxygen. It starts giving off methane gas, that's the green one, and then that goes over into a methane furnace, a boiler, makes steam. You use the methane as a natural gas, right? You light it and burn it, and then that drives microturbines that generate low voltage direct current. Just pipe that in, use that to offset your grid costs, and the CO2 byproduct of anaerobic digestion plus the combustion of methane, that can be filtered and can be used to offset some of the bottled CO2 that they're now pumping in. So potentially you could close the loop here. You could close the vents on both ends of the warehouse. You could also use some of that renewable energy to power air conditioners, to condense the water vapor and recycle it back to hydroponics. So this is borrowing the lesson from NASA again, from that closed loop life support system, from that model analog of Earth's biosphere. Close as many loops as possible, and this is what we really need to do in the next 50 to 100 years to make indoor agriculture both profitable, productive, and sustainable, this sort of thing. So keep going back and forth to the NASA lessons and trying to apply them to ground-based earth agriculture. So with that, our time is up, and I'll be happy to entertain any questions. Right here?
On the International Space Station, where you showed they're growing food, is it truly a closed loop system?
No, not at all. The closed loop thing is for the future. It's for the lunar outpost. It's for the Mars base. We're just thankful to have plants back on NASA's radar. So in fact, there's a problem there on the International Space Station and the veggie environmental conditions are open to the ambient space station cabin conditions. So it's low humidity, it's not the best for plants, and the carbon dioxide is very high. It's around 2,800 parts per million up there all the time. And when we tried to grow Chinese cabbage to grow up there, it would not tolerate that. So it's very interesting. Different species and different cultivars seem to tolerate extreme conditions differently. We're growing Mizuna hydroponically in these veggie analogs now, and it tolerates the space station level CO2 better.
What is Mizuna?
It's a Brassica rapa. It's the same species as Chinese cabbage, but one tolerates high CO2, the other doesn't.
How does gravity affect the plant growth? You're out, on the space station or on the moon or Mars, you're going to have different gravity effects.
That's a great question, and that's one that the space biology program has been trying to address for 30 years. Plants will grow. They grow with less lignin. They grow more weakly. They often do epinasty of the leaves in weightlessness. That's not necessarily good. They're not presenting their maximum area to the light. Sometimes there's too much water in microgravity. Capillary action is forever. And so you have to really compartmentalize off water, roots, and nutrient solutions from the top, because it'll just float. Basically, they will grow, but whether they will grow as productively as we need them to grow, as productively as we can get them to grow on the ground, this remains to be seen. And what level of gravity? I mean, Mars, lunar gravity is about 1/6 Earth normal. Mars is about 3/8. At some point, it'll start to normalize, but we don't have data yet to know that.
It seems like in the future that the people who explore Mars and the moon will have to be vegetarians. Will the vegetables have the same nutrient values as they have here, or not? Or will there
Yeah.
be a different species of vegetable that they'll have?
Well, those early NASA scenarios were for a vegetarian diet, obviously.
Potatoes.
There have been, in Biosphere 2 in Arizona, they did actually have some poultry and some small animals that were consumed, but that's not on Mars, that's in the Arizona desert too. But diet and nutrition will be all important, however, because there's a lot of stresses in space. And one thing that was found some years ago to ameliorate some of the space radiation sickness effects was blueberries. They could protect against some of the damage that I don't see growing woody blueberries necessarily up there, at least not now or for a long time, but they're finding out that nutrition is extremely important. And just taking vitamins and antioxidants in pill form that the astronauts do now, it's not available enough. They're going to need fresh vegetables to get the phytonutrients they need. We're not there yet, just in the early stages of this. But I think my main message here today is that while we're figuring all that stuff out for space destinations, the emerging field of controlled environment agriculture is already benefiting from the original NASA-sponsored research and that which it has spawned on its own now.
Wow.
Don't want people getting scurvy.
Scurvy?
Scurvy.
Vitamin C deficiency.
Fresh fruits and vegetables.
Well, yeah, I mean, that's what they used to get on the old exploration wooden ships, didn't they? They didn't have enough fresh fruits and vegetables. So could astronauts get that? Possibly.
So besides NASA, what other entities are interested in sponsoring this type of research?
Yeah, well, finally, USDA NEFA is finally starting to wake up. And this year in Washington and thereabout, they've had a couple of conferences already about developing funding for the vertical farming industry and for the CEA industry. So I think it's coming on the radar screens. And even NSF in its Infuse program, Innovations at the Nexus of Food, Energy, Water, even NSF has discovered agriculture. So I think it's right at the, it's about to explode. That's what it is. Okay, thank you.
Wow.
We'll get the Kiwanis later to talk today, Cary.
Thank you, Gus.